maths educational video. Let me show you two examples on the use of the fundamental theorem of line integrals. First, let's recall what this theorem is about. If you are given a conservative field, which is the gradient vector of some scalar function f, and you are given a curve connecting 2 points. The initial point is r of a, and the final point is r of b. Then the line integral of f over the curve c is given by this expression, which is the difference of two numbers. One is the potential function f evaluated at the terminal point, and the other one is the function f evaluated at the initial point. Interestingly, the path c is not involved. In the first example, we look at a two-dimensional field. Here we are given a conservative field because capital F is the gradient vector of the small f, which is given as x, y. We are also given 2 points, a, b. So our job is very simple. All we have to do is to apply the theorem. But first, let's find out what the initial and terminal points are. That depends on how the question is phrased. Here we are told that the curve is joining A to B. So A will be the initial point, B the terminal point. So it's important to know exactly which is which. So applying the theorem directly, we'll evaluate this potential function at the 2 points. At the terminal point, we have x equals to 2, y equals to 3. So you'll substitute this xy into the formula for f. So you get 2 times 3 equals to 6. As for a is minus 1, 2. So you get minus 2. So the outcome is equal to 8. Here's an important remark. If the question says the point C, the curve C joins B to A, then B will be the initial point and A the terminal. The answer will become minus 8. Example 2 is more complicated for two reasons. Number one, this is a 3D field, so much more work is expected to be done. And secondly, we are not given the potential function. So in this example, I will show you the method for doing so. To find the potential function for a conservative field in a 3-dimensional space. We have done a similar example in the 2D space. And as you soon find out, the method is the same. We begin by writing the given vector field as a gradient vector of some unknown scalar function f, the potential function that we wish to find. What follows next will be obvious. We do a term-by-term comparison to write down 3 equations. Comparing the I component, we get equation 1. Similarly, comparing j and k, we get equations 2 and 3. And we will use these equations one at a time. Starting from equation 1, what we have here is a differential equation. df dx equals to some expression. So in order to get f, we have to perform an integration. So we will integrate both sides of equation 1 with respect to x. And now we can do the so-called partial integration. When we do integration with respect to x, the other two variables y and z will be regarded as constants. So for example, sin y will become x sin y, because sin y is now treated as a number. Let me make an important remark about the arbitrary constant. Instead of just writing a number a, you should write a as a function of y and z. And that's because we are doing partial integration. In the presence of x, in the presence of z and y, the constants will have to be in terms of these two unknowns that we treated as constants. So it is something we have to keep in mind. So if you are doing integration with respect to y, then xz will be the constant. So in that case, your arbitrary constant must involve x and z. So the rule is that the arbitrary constant must involve those unknowns that you consider constants. So far we have obtained an expression for f in terms of x, y, z and these unknown integration constants. So we will now use equation 2 to solve for these constants in red. We will differentiate, according to equation 2, we will differentiate y, f with respect to y. So we will do the partial differentiation of the formula in green and form this equation. And now you can equate the expression here with the expression that you see in equation 2. So we expect this term in the green box to be equal to x cosine y. And now if you do a comparison, you can see that d over dy of ayz equals 0. Now what's the meaning of this? Ayz is supposed to be a function of y and z. But when you differentiate with respect to y, you get 0. So the conclusion is ayz actually doesn't depend on y. And therefore you can write ayz as a of z only. Because now we are sure it doesn't involve y, it involves probably only z. So what we have obtained so far is the function f in terms of x, y, z and this unknown constant az. Obviously we have to deal with this term az. So it's time to use equation 3. We differentiate the one in the orange box with respect to z and equate this outcome with what you see in equation 3. And now comparing these two expressions, we conclude that a prime z equals to 0. And again, because the derivative of a with respect to z is 0, we conclude that az is independent of z, which means a of z is actually equal to a number. And that's our conclusion. Any potential function f will look like this. There's no way we can solve for a, because if you can remember, if f is a potential function, then f plus any constant is a potential function as well. So the answer for potential functions is always one involving an arbitrary constant, free of any variables. With the potential function at our disposal, we can now compute the line integrals. Although the parametric equations for the curve is given, we know that it is not required. All we need are the 2 points, initial and terminal. And now we apply the theorem. We evaluate the potential function f at these 2 points and subtract them. And we get the answer 2 pi.